Hey guys, now that we have finished stoichiometry, the unit on stoichiometry anyway, you will still see some stoich in what we're doing. We're going to move on to gas laws. And the first part of gas laws is learning about the properties of a gas. So you need to open up your notebooks, make sure you're ready to take some notes, and get yourself settled in. Okay? As you're going through the video, feel free to pause and back up in case you miss something. So we're going to start with the nature of gases. Okay, we know that gases are one of the states of matter. They've been studied for a really, really long time, over 300 years or so. And the first gas that was studied was air, which is obviously very prevalent around us, right? That's what we need to breathe. And it was discovered that air was actually a mixture of particles instead of a single gas. So air is made up of things like oxygen and nitrogen and hydrogen and a lot of the different elements that we know of to make up what we breathe. Now you might think that realizing that air is a mixture of gases instead of just a single gas would make everything more complicated. However, it didn't. Gases behave the same whether it is one gas or a mixture of gases. So they follow kind of the same properties and they have the same behaviors no matter if it's one single gas. For example, oxygen could be a gas. What's another single gas we have? We've got oxygen, nitrogen, hydrogen. If you remember all of our Han and the halogens, all of the ones that are diatomic, chlorine, fluorine, okay? And then we have all of our noble gases, of course, as well. Neon is a noble gas. Helium, okay? Those are all noble gases. So they follow the same behaviors as any single gas, regardless of their chemical identity. So no matter what the gas is, if it's oxygen, if it's helium, if it's neon, if it's nitrogen, they're going to all exhibit the same kind of physical behaviors. So that means they're going to do the same kind of thing. So they're going to behave the same. Gas particles, there's a variety of different types of gas particles. So they can be monatomic, which remember mono means one. So they can be one, and atomic means atom. So one atom, such as neon, right? There's only one neon here. They can be diatomic. So if you remember that di means two, so it's two atoms, just like N2, that's where that little 2 comes from. Or they can be polyatomic, like CH4, which is methane gas. That's the stuff that comes out of the Bunsen burners in our classroom. Poly means many, okay, so it's made up of many atoms. So if you look at CH4, you can see that there's one carbon atom and 4 hydrogen atoms. So there's obviously more than one atom that's there. Even though these are 3 different ones, they all have the same characteristics in common. Okay, the first thing that they all have is they have mass. What does that mean? That means you can weigh them, right? You have grams. They are compressible. Well, what does it mean if you compress something? If you compress something, it can be pushed together, closer together. Gases will always fill their containers. So you can kind of think of a balloon. If you blow air into a balloon, what happens? They fill up the balloon. Gases diffuse. That means that they go from an area of higher concentration to an area of lower concentration. They will always spread out because the particles, once they're close together, they want to get away from everybody else, so they spread out. If you think about spraying perfume in the corner of a room, eventually it will diffuse into the rest of the room. Gases exert pressure, so they can put pressure on things, and pressure is going to be dependent on the temperature of the gas, okay? If it's a hot gas, the pressure will be different than if it is a cold gas. We use a theory to talk about the behaviors and characteristics of gases, and this is called the kinetic molecular theory. Now we can break this down and figure out what this is talking about, because these words are a little bit new. Okay, kinetic, though, you've probably heard of kinetic energy. That's the energy of movement. The word kinetic is talking about motion. So when we talk about the word kinetic, we're always talking about motion. okay? The word molecular is talking about the molecules. So that could be a molecule of nitrogen, N2, or it could be a molecule of oxygen, O2. So anytime we talk about molecular, we're talking about molecules that are there. We can also say that kinetic molecular theory is going to talk about the motion of molecules. In a nutshell, the kinetic molecular theory states that the tiny particles in all forms of matter, we know that matter is made up of tiny particles, right? We have those atoms. The kinetic molecular theory states that all particles are going to be in constant motion. So they're always moving. In a solid, they're going to be more compactly in a space, more compacted in a space, but the particles are still moving. They're just closer together, so they can't do a lot of movement. Whereas in a gas, they're spread out more, so there's a lot more motion that's happening. This theory is used to explain the behaviors amongst most gases. So almost all gases are going to react the same way. And we have three basic assumptions of the kinetic molecular theory as it applies to gases. These assumptions are things that we assume will always happen no matter what gas we're talking about, whether we're talking about oxygen or helium or neon or hydrogen, any of those types of gases. The first assumption is that a gas is composed of small, hard particles. Okay, so there's small little particles that make up the gas, right? Composed means make up. The particles have an insignificant volume and they're very far apart. So the distance is talking that they're far apart. They're not close together in a gas. Whereas remember, in a solid, particles are more closely packed together. Between the particles in a gas, there's empty space. So there's nothing in the way. So they're just kind of bouncing back and forth. And then there's no attractive or repulsive forces between particles. Well, what does that mean? They're not attracted to one another. They're not like magnets. If we have two magnets that are close together and they're opposite poles, they attract. Or if we've got the same poles, they repulse each other, right? They repel. This doesn't happen with gases. They have no sort of charges that we deal with. The second assumption of the kinetic molecular theory is saying that the particles in a gas move in constant random motion. Okay, when we talk about constant random motion, we're saying that they're always moving. They're always moving. They're going back and forth, back and forth. If you think about a classroom, okay, their air is bouncing back and forth, okay, air molecules. And once they hit a wall, what do? Well, they bounce right back out. If you think about like a pool table with pool balls, and they hit the end, and then they bounce out again, and they hit the end. And if they hit another ball, they bounce in a different direction. So it's just everything is bouncing back and forth. That's what constant random motion is. There's no pattern that's there. Particle moves in straight paths and are completely independent of one another. So they're really not concerned, the particles, with each other. If they happen to bounce, run into each other, then they bounce back apart in a different direction. And then the particle's path is only changed by colliding. So collisions are what make the particles change their path. Otherwise, they stay in a complete straight line path going back and forth. So if we had one particle in the classroom and it was just bouncing from the front wall to the back wall and nothing got in its way, it would just keep going back and forth, back and forth. The last assumption of the kinetic molecular theory is that all collisions a gas particle will undergo are elastic. Well, what does elastic mean? Elastic means that basically they hit each other and they bounce apart. They hit each other and they bounce apart. So there's no energy that is lost from one particle to another. It's not like one particle says, oh, I'm going to go faster, and then I transfer my energy to the other gas particle. Nope. They bounce together and then they bounce back apart, and they have the same amount of energy as they did when they hit. So we say that no energy is lost, and the total kinetic energy is constant. It doesn't change at all.